All right. Good morning. Good morning, Leah. Good morning. Okay, so I'm standing in front of third hour, so if you hear them giggling or whatever with my headphones and microphones, so that's a really good image of you guys to have. And I'm going to record this live, so since you missed class today, you guys will know what's going on. So we are listening starting here, and we listen to the podcast about Q. Who can tell us what Q is? What does it say? Reaction quotient. And you're going to see today what it means and how we have to shift things. And K, if you write the expression for K, what is K equal to? Products over reactants. Products over reactants. And so we're going to generate Q so we can figure out which way to shift. And this will make more sense in just a second when I show you the example. But if Q is equal to K, what do we know we're at? Equilibrium, so our teeter-totter is even, right? And then if Q is greater than K, it says that we need to shift it to the left, because if Q is greater, what do I have more of? Products. And then the opposite for that. So if you guys go straight to the end of your, you guys don't have to flip here, but this is exactly what we did on the very last page. That didn't make too much sense when I did it the first time. So if K is much, much greater than 1, you can see I have more product. If it's less, I have reactants. And again, this is just what we talked about, but this teeny little trick down here at the bottom will help you out. So you can see the little alligator. You guys have been called the greater less than sign as an alligator probably in elementary school, right? And so the reaction quotient proceeds to the left because K is going to eat Q, do it in that direction, okay? And then Q is going to eat K, so we're going to proceed to the right. So it's just an easy way that if you write Q is greater than or less than equal to K, we know how to shift it. Okay? So now let's apply that little alligator. So the first thing we're going to do is, yes, this is where I think we want to be. Is that the next page? Okay, so the first thing we want to do is we want to do this solving process called ICE. So above it, I kind of squeeze mine in right at the top. You guys do the same thing. So we're going to call this ICE tables, and we're going to use this for the next couple of chapters. So ICE stands for initial change, or initial concentration, sorry. C is going to be the change or shift, and E is going to be our equilibrium expression. So we're going to use ICE tables in equilibrium, in acid and bases in the next couple of chapters. So the first thing we need to do is we can't get away from writing our balanced equation, so let's do that. It says a reaction of hydrogen gas and fluorine gas produces hydrogen fluoride gas. Both the reactants and products have a concentration of 2 molarity. Find the concentrations of each at equilibrium. Okay, so what do we know about, how do we write hydrogen? H2, fluorine, F2, hydrogen fluoride, HF. Okay, so let's jot that down. And again, they are gases, and what do we know about gases and the equilibrium expression? Do we get to include them? What don't we include? Okay, but we include aqueous substances, all right? So solids and liquids. Okay, so these are gases, so we're going to include it in the equilibrium expression. And it says they all have the same initial concentration. So this is going to be ICE, I-C-E. So our initial concentration for all of these is 2. Is our molarity. Okay, so if we apply Le Chatelier's principle, does this tell us which way to shift it at all? No, we can't tell. If I were to add more hydrogen, we'd know it'd shift right. If I remove HF, I know I'd shift right. If I add more of this, I'd shift it left. I have all those scenarios, what we just talked about, but because the concentrations are the same, I don't know what to do. So then we have to calculate Q. That's the reason for the reaction quotient. Okay, so our equilibrium expression, I have to tell you what K is, and I must have looked it up. I forgot to type it in here. So K is equal to 1.15 times 10 to the second, and we know that it's product over reactant, so it's the concentration of my hydrofluoric acid squared over my concentration of fluorine to my concentration of hydrogen. So can I go ahead and calculate Q really quickly by putting in my values? So let's do that. So Q is equal to 2 squared over concentration of fluorine, concentration of hydrogen. So this equals 1. Yes, Becca. I looked up K. It should have been given in the problem. I should have typed it in and said that the equilibrium constant is. Okay, they had to give us a little bit more information than what I had here. All right, so here's Q and here's K. So if I write this, Q is what? Greater or less than K? Less than, right? This is 115, this is 1, so it's less than K. So which way do I need to shift it? To the right. Q is going to eat K, and this means that I have to shift it to the right. So I need to make more products. So I'm going to shift right. Okay? All right, so what does that mean? So if I'm going to shift it right, does it make sense to you that F2 and H2 are going to decrease if I'm shifting it right? So I don't know by how much, so I'm just going to say X. So this is going to decrease by X, decrease by X. What's the other side going to increase by? X or 2X? Why is it 2X? Yes, because there's a mole ratio there of 2. Yes. Because their mole ratio is 1 to 1, and so their concentrations are going to change by the same rate. If I had 3 right here, then I would put minus 3x. Yeah, yes. Always going to be x, they're both going to be x, and we just differentiate the variables based upon the coefficients in front. Okay? All right, so I have my initial concentration, I have my change. Now I'm going to write my equilibrium expression, and sometimes I kind of think of it like this, where you're adding them together. So now it's going to be 2 minus x is this expression. This one's also 2 minus x. And then this one is going to be 2 plus 2x. Now this is where we get to do all this lovely algebra that you guys love to do. So now what do? Can I put this into my equilibrium expression, figure out what x is, and then can I figure out what the concentrations are at equilibrium? That's what we're trying to do. How do these change to get them into equilibrium? So I'm going to put it into my expression. Have you guys been writing small? Do you have more room? Okay, so continue right here in this spot. I'm just going to put it to a new screen so you guys can see it. So I know that my equilibrium expression is 1.15 times 10 to the second, and I have to square my HF. So I'm going to take 2 plus 2x. Do I square that? Okay, over my concentration of my fluorine and my hydrogen. So my expression for my fluorine was 2 minus x. My expression for my hydrogen gas was also 2 minus x. Now do I just go to town with algebra? Yes. The top is squared. We asked why the top is squared because of our expression right over here. You can see that it's a hydrofluoric acid raised to the second power because the coefficient is 2. And then this is 1 and this is 1 because the coefficients are 1. Okay, so then we need to go ahead and we just need to continue to solve this. And I did this. I did 1.15 times 10 to the second. I left this squared. I have the same expression on the bottom. Is that also squared? So if I see that, what can I do? Can I take the square root? Yes. So that's what I did. I took the square root of this. I can't just do it on one side. I have to do it on the other side. So I took the square root of both sides. And then I got, let's see, 10.72, 2 plus 2x over 2 minus x, because that's going to drop. And then do I need to continue to do my algebra? So now what am I going to do? Okay, so I'm going to cross multiply, basically, right? So I'm going to multiply that in. And let's see what I get for that. I got 21.44, subtract 10.72x equals 2 plus 2x. Combine like terms, and I got 19.44 equals 12.72x, and x equals 1.53. Okay, so we're going to be doing lots of algebra in this chapter, as you can see, and this is an easy one to do. Yes. Well, we're not done yet. Okay, so do you agree that I got my x? Okay, so the question is, what are the concentrations? Find the concentrations of each at equilibrium. That's what our goal is. So do we know the expressions at equilibrium? So now can I just substitute my 1.53 in here as my x, and would I find the concentration of each one of these when my teeter-totter is level? Right, it's just your initial concentrations. And then you're going to put these in this closed system, and then they're going to start colliding with each other. And remember, when we think about equilibrium, I want you to think about that half-filled water bottle. So in the bottom of the water bottle, we have this fluorine and hydrogen. They're banging against each other, making collisions. Maybe up above, we have this hydrofluoride gas, and they're making collisions. It's gaining energy, releasing energy, going back and forth until that teeter-totter's even. And then what is that concentration of them at that point? Does that help a little bit? Keep that picture of the empty water bottle. I know an empty water bottle isn't a solution. It's not a concentration. It's not a reaction. But you can imagine the water molecules colliding in the liquid phase, changing to the gas phase, from the gas phase back down, back and forth. That's equilibrium. How are they getting that teeter-totter even? So in here, this is all reacting in whatever vessel they have it in. And now I need to take 2 minus 1.53, and that's going to be the concentration of fluorine, and happens to be hydrogen because their expressions are the same, at equilibrium. Okay? So our final answer then is hydrogen, concentration of hydrogen is equal to the concentration of fluorine, and I took 2 minus 1.53, and that's going to be a concentration of 0.47. All right, so that's my reactants. And then on my product side, my concentration of hydrogen fluoride is 2 plus 2 times 1.53, and I got that to be 5.06, and I know I'm not really paying attention to significant figures very well. We could go back and do that. They're not going to be fussy about sig figs at this point. Now, could I check my answers? Maybe I do all this math and I'm not very confident in my algebra skills because that was way back in 8th grade and that's a long time ago. Could I figure out if I did it right? What would I do? Okay, if I plug these values into here, should I get 1.15 times 10 to the second or relatively close to that? So if you go through all your calculations, you're like, I'm just not very confident, throw them in there. That takes a second to figure that out. Okay? All right, how's that? Good? Okay. So I want to do another one that has quadratic, and then we're going to try to do one in our book. Okay? All right, so we're going to do the same thing right here. We're going to do example 1. We're going to use a quadratic formula. If you have a solver in your calculator, you could do it that way. We really aren't going to do many with the quadratic formula. There's a way that we're going to jump around that by simplifying things a little bit. But we need to show you that and try one and assign another one just to make sure that in case they do give you one with a quadratic formula. Okay, so here's our beginning information. I am giving you this, and the gaseous phase is going to decompose into iodine gas plus bromine gas, and I'm going to tell you that the K is 8.5 times 10 to the negative third. Okay, so this is our initial. I know I don't have it all written out, but we want to find out what each one of them is at equilibrium. And I'm going to give you the initial condition. So for our ice, our initial concentration here is 1. This is going to be 0, and this is going to be 0. So basically, I am decomposing iodine monobromide with a concentration of 1, and no product has developed yet. This is how you're going to see a lot of them. Sometimes you won't have to calculate Q at all. Why don't I have to calculate Q? They're not all the same, okay? So do I know which way this is going to shift? It's going to shift to the right. I got to make some product, right? I got to make some product, so it's going to shift right. So is the left-hand side going to decrease? So this is going to be minus what? For the change, minus 2x. Why is it 2? Because the coefficient out in front. Okay, so minus 2x. And then what's the other side going to build up by? Positive x, positive x. And those are x because the mole ratio in front of them is 1 to 1. All right, so then I can write my expression. So it's going to be 1 minus 2x. And this is just going to be x and x. Okay, so my equilibrium expression. So I have K is equal to 8.5 times 10 to the negative third. I know that it's the concentration of iodine times the concentration of bromine over the square of the concentration of iodine monobromide. So I can go ahead and substitute in my equations. So this is going to be x times x, so this would be x squared over 1.0 minus 2x squared. Why can't I square root this one? Can't I? Mathematicians in the room? I think it does too. I have this as an example that it's supposed to be use a quadratic formula, but let's walk through it without it and let's see if we get the right answer. Because I would just square that. Square root it, I mean. Is that what you would do? Okay, so someone get out their calculator because I obviously do not have it worked out this way. So if I take the square root of this, I would take the square root of that. So what is the square root of 8.5 times 10 to the negative third? Say that again. 0.092. Okay. Over x squared. No, that would just be x, right? Is that right? Okay, then let's cross multiply. So I would get this times that is 0.092 minus 2 times 0.092 is what? What is it? That's not it though. 2. Oh yeah, that's right. X. So I'm going to add, so this would be 1.184x, right? 0.092 divide by 1.184. Sam, what did I get? works. Yeah. Yeah, let's avoid the quadratic if we can, right? Okay, so that's my x. Am I done? No, we're not done. You need to substitute it back in and figure out the concentrations of each of them at that point. So I'm going to take 0.078 and I'm going to put it into my expressions here and find my resulting answers. So iodine and bromine are going to be this answer x. So my iodine concentration is equal to my bromine concentration. And that's what my x is, so that's easy to do. So that's my answer there. At equilibrium, that's the concentration of that. And then my concentration of IBr is equal to 1 minus 2 times my sig figs might be off on this one because I had an extra sig fig. So did you calculate this right here, Becca? 0.844. Okay, so these are my concentrations at equilibrium. This is what my equation would be like when I have just as many going forward as I have in the reverse. So my teeter-totter is balanced. Okay? Okay, so let's try this. I want you guys to go to, we got to do 2 problems. So I want you guys to do problem number 33 and 48. So I'm going to turn this off for you guys that are listening, but we are going to do page 615. We're going to do number 33 and number 48. You can try those, bring them in, and I will check them and see how you did on those. Okay, I'm going to pause this. I'll come back to you if there's something we need to come back to.